glaciers, glacial processes, but I can, convincingly say that Wisconsin is world class. We have features here that people travel from all over the world to come and look at when they're going to understand how glaciers work, right? And the act of glaciers in Wisconsin over the past has heavily influenced what Wisconsin looks like when you drive down the road and you see a hill or you see a valley or you see various trees of certain tree types. It's a pretty safe bet that a lot of that has been influenced by the glacial history of the state, how it's built things up, slowed things down, and shifted things around. And so this is a picture, for example, of not Wisconsin, but it's Iceland, right? And this looks interesting, but it's probably not that different, for example, than Wisconsin was 15 or 20,000 years ago. I have a big glacier here. It's flowing down in this direction. You have these big piles of sediment right here. You have these lakes that are in between it. There's not a lot of vegetation because there's so much sediment in these glaciers like that and retreating over this area and screwing up whatever would have started to grow there. And you have these big bridges right here you can see that are formed. All of these are put in place by the glacier moving sediment, right? It's tearing up, it's moving around what's at the bottom of it over time, and it's building piles in some areas and it's digging out other areas over time. And you can imagine if you gave this landscape a few thousand years, the vegetation started to grow on it, it would look very similar to what you have right here in Fond du Lac. It's not that different, actually very similar to Fond du Lac. And so today, what I want to do is talk a little bit about like how glaciers have advanced or retreated over the state, and then spend some time talking about the way that they've actually shaped the state, the way they've built things up with this and torn things down with this. And then zoom in a little bit to this area, Fond du Lac County, and draw out some specific things that are similar to what I'll show in the rest of the presentation. So I guess the fundamental question is why does Wisconsin look like this? Okay, so here's the state. If you look at it, this is what's called a shaded relief map. And so it kind of shows the topography. It shows where there's areas that have high highs and low lows, like part down here called the driftless area. And you can see that other parts of the state are maybe more subdued. They don't have as extreme of relief as we see in the driftless area. So one fundamental and easy question you might ask is why is this part of the state look all wrinkly like this? Why does it look like it's been carved a lot differently than, for example, the rest of the state? And so we call this the driftless area right here. And this is the rest of the state was glaciated in the last time period that the glaciers were here. And so a lot of this has to do with the part of the state that was covered by glaciers, this part, and the other part of the state that wasn't covered by glaciers. And so we'll talk about that for the rest of the time here. Talk has a couple different components. First, we'll talk about ice ages in Wisconsin. How has ice advanced and retreated over the state over the last several million years? How does glacial erosion occur? How do we carve out the landscape and move sediment around? And then how do we move that sediment that we've carved? And then lastly, we'll talk about glacial land. When I say landforms, what I'm talking about are those individual features, like that pile of sediment in the one instance, or the hill that was dug out in sort of another instance. We'll split this into sort of two big categories: subglacial landforms. These are things that are made underneath a glacier, and proglacial landforms. These are things that are made right at the edge of the glacier, right where the glacier stops, just in front of it. So first, ice ages in Wisconsin. When geologists talk about time, they use the sort of weird way to do it. They use these big time scales, and the time scale is purely that's because way back in time, we don't know that. So it's hard. We don't break it up into as many small pieces because we don't know enough to break it up into small pieces. As you get closer and closer and closer to the modern day, we have more and more information, more and more rocks, things like the landscape. We break it up into finer and finer detail. And so this is just part of the geologic scale. You can go from 65 million years ago up until present day. And this is called the Cenozoic. And for this talk, all you need to know is we don't care about any of this, except for this little part right here. This is when we had glaciers the last 2.5 million years, when we had big ice sheets that grew on North America, and they waxed and waned and waxed and waned. In particular, the Quaternary has two components, the Pleistocene and the Holocene. Pleistocene is like 2.5 million years ago until about 10,000 years ago. That's when we have big glaciers. And the Holocene is the last 10,000 years when we haven't had big glaciers. And so in particular, this Pleistocene is the thing that we'll talk about. This is the time period where big glaciers have grown on the landscape in a place like Wisconsin or North America. And most of the action has been done to shape it over time. So the Pleistocene is dominated by these repeated glaciations or ice ages. In total, there was about 30 of these. But what I mean by that is giant ice sheets grew on Canada. The ice extended down into Wisconsin. Then the climate would have warmed, and those ice sheets would have gotten smaller. And the ice would have retreated out of Canada, and then it would have grown again. The ice would have extended. So that's happened like 30 times. And how do we know it? It's hard to figure that out when actually looking on the land. Because every time the glaciers grow and re-advance, they wipe out most of the evidence of the previous one. So the way that people have known that it's grown and contracted 30 times is they go in the ocean and they can take cores of sediment from the ocean. They can record deeper in time because in the ocean, things aren't erased. You just continually add to it. And so people have gone into the ocean and they've collected sediment cores and they found these little organisms in them. These organisms record information in their shells to tell us how big or small the ice sheets would have been through time. And this wiggles here sort of trace that. Every time the wiggle goes down towards the bottom, so this is time. This is 3 million years ago until 0 now. And every time the wiggle goes down, we have a big ice sheet on the landscape. And every time the wiggle goes up, the ice sheet goes away, essentially. And you can see there's a bunch of wiggles here. Then about 1 million years ago, we get these bigger wiggles. They're going up and down. And you can see we went down into this one. This was the last time there was a big ice sheet on North America. This is the one that was called the Wisconsin glaciation and shaped Wisconsin because Wisconsin is the place where it's best preserved. And then as we went into that Holocene and things started to warm up, we got to the condition we are now. We don't have big ice sheets. So this is a kind of a cool video from, this is 20,000 years ago. So this is just the Wisconsin glaciation. And this is how this big ice sheet that was centered over Canada called the Laurentide sort of slowly disintegrated in response to that warming that was going on. You can see these different loads of ice that we call them, these fingers of ice that are coming out of the big glacier are waxing and waning and waxing and waning as it goes away. And this is sort of the end of it, the death of it, right? So we're at 5,700 years ago, 1,000 years ago, this is basically where we're at now, right? And so this big ice sheet that existed on the landscape has gone away in sort of the last 20,000 years as the climate is slowly. Now that last ice age, the one I was showing there, is called the Wisconsin Ice Age. It extended from 75,000 years ago to 12,000 years ago. A lot of times it's called MIS2. If you were really paying attention, you might have noticed there was a 2 on the previous one. That's why they call it there. The reason it's called the Wisconsin Ice Age is because this guy, T.C. Chamberlain, who was a geologist, a glacial geologist in the department at Madison, and then went on to become the president of the university, sort of discovered, or he put enough of the evidence together to be able to recognize that it existed. There's an older ice age called the Illinois Ice Age. That would have been the one big ice age before it, the big glacier right before it. And then there were a bunch of ice ages before that that we don't really know that much about. We just lump them all together and call them pre-Illinois. And that's because on the land, like I said, all the geologic evidence that that glacier was there was wiped out by the later glaciers growth. So we have really good evidence for this. So good, in fact, that in Wisconsin, the land, the evidence for on the land is so good in Wisconsin that the ice age was named the Wisconsin Ice Age. That's what they call it everywhere. It's not just in Wisconsin. It's called Europe, New Zealand, everywhere. Wisconsin is the best example of the ice age that we have in the world. The Illinois one, because that one extended a little farther south and it's preserved in Illinois. It then is older. So just take it closer to home. This is that same type of diagram, but it's much more accurate and it's Wisconsin's central, basically. This represents probably the cumulative effort of 3 people's careers that worked on this for 40 years to build up enough information to be able to figure this out. What you're seeing is it's counting down 20,000 years ago, 19,000 years ago, and it's showing the waxing and waning of these glaciers that moved to Wisconsin. I put a little star here for where we are on the way. You can see that, you know, if this re-advance and retreat, this thing will click over here and restart in just a second after the ice freeze. Right, but 31,000 years ago, the ice reaches its maximum extent, and then it sort of retreats. But you can kind of notice something here. It's not like a gradual retreat. It doesn't just slowly move out of the state. It goes away, and then it comes back, and then it goes away, and back, and it goes away, and it comes back. So even when it's moving or decreasing over time, there's lots of phases of pulses associated with it. You can see the big blue areas here and here. These are what are called proglacial lakes. They're temporary lakes that are only there because the glacier dammed the water. And where we're sitting right now is on the footprint of one of these giant glacial lakes called Glacier Lake Oshkosh in Fond du Lac. And that's what you dig a hole right under this library. That's what you would find is sediment from this one of the old proglacial lakes that covered this area. So we give these different fingers of ice that come off the Laurentide their names. They're probably recognizable to you, even if you've never heard of them. The Lake Michigan lobe. It basically sat in Lake Michigan, and it's the thing that carved out Lake Michigan. There's a Saginaw lobe that's over sort of carved the Saginaw Bay in Michigan. And we have this one right here that's what we're sitting under right now, which is called the Green Bay lobe. It carved out Green Bay. It sort of extended all the way basically down to Madison, where it stopped. And right here, we would have been squarely under the footprint of the Green Bay. Then we have this huge lobe to the north called the Lake Superior lobe. It's what helped carve out Lake Superior. It wasn't the only thing that made Lake Superior, but it really helped sort of deepen the basin. And there's other sub-lobes, we call them, associated with really big ones that I don't think. So this spot, this is just Wisconsin. So here's the Green Bay lobe. You know, we would be somewhere right about here right now. Here's the Lake Michigan lobe. It extends all the way down into Illinois. The Lake Superior lobe is up in the Lake Superior Basin. And there's all these little sub-lobes that are coming off it as well. Think of these as small little fingers of glaciers. Now, I'm saying small, but these are enormous, right? When you see a glacier in Alaska that looks like it's, you know, absolutely monumental, it might be as big as the B in the lobe. These are so much bigger than the things that you see in places like Alaska or New Zealand. These are continental scale glaciers. So just warping the scale of like things that I showed, for example, in Iceland too. So when you look at this footprint in the map, you can kind of see those lobes in it, right? You see this boundary right here, that's the Green Bay lobe. See this boundary right here, that's the Lake Michigan lobe. These areas up here are the more northern lobes that are associated with Lake Superior. And this is the part right here that was missed, right? This is the part that was never glacial. It's the only part of the upper Midwest that wasn't covered by glaciers, which is why the sort of the texture of the land surface in the Grizzlies area is so much different than what you find in Minnesota or Michigan, most of Wisconsin in general. So how does it get to that, right? What are the glaciers actually doing to change the landscape to make it look differently? For example, in areas that was glaciated, than areas that it wasn't. What is the processes that it's using to grind up the rocks or move the sediment around that it's ground up? Well, one thing to realize is that glaciers are always flowing. They're basically like a slow motion river. So this is a time-lapse video of a glacier in Asia, and the ice is flowing from a high elevation down to a low elevation, just like a river flows from a high elevation down to a low elevation. And it's carrying ice with it, right? So when you look at a glacier, it looks like a big stagnant mass of ice, but over even relatively reasonable timescales of just a year, you can watch it move sediment, or you can watch it move ice from the high elevations to low elevation. But it's also carrying sediment, right? It's grinding up the rocks that this mountain is made up of, and it's transporting them. In this case, it's dumping them down at the end. And so it's like a conveyor belt where it just keeps moving sediment that it grinds up from the high elevations down to the low elevations. Looking at it from the side. So this is, instead of looking at it from the top down, you can look at it from the side. You can see there's a zone of accumulation where ice and snow accumulate. And then over time, that ice flows downhill slowly. All the while, it's grinding up the bottom of the glacier, or the bottom of the bedrock that's beneath it, by processes like plucking and abrasion. And it's taking that material that it's breaking loose from the rocks, and it's carrying it down and eventually to hollow at the end. So this is what the bottom of a glacier actually looks like. Yeah.
How thick were these glaciers at the time?
So 2 miles, maybe thicker. In some areas up by Hudson's Bay, they would have been thicker than that. In this area, they probably have been just under a mile. Yep. So this is what the bottom of a glacier actually looks like. It's not pure ice. There's clean ice. This is dirty ice, and this is bedrock. This is a glacier in Norway. The Norwegian government's drilled a tunnel underneath the glacier, and you can walk up under the glacier. You use a giant, basically squirt gun that you have in a car wash, and you can melt open a hole at the bottom of the glacier and see what it looks like. That's right, this picture of it's like this is the actual where the rubber meets the road, where the glacier is sitting on the bedrock in this case, right? So you got to imagine that as it's moving, as the glacier is flowing, for example, this way, all of this stuff, all of this debris that's in the ice is being dragged over that bedrock, right? And you can imagine that's probably doing something to erode the bedrock, to shave it away, just like sort of sandpaper on a board. That's effectively what happened, right? Is as that glacier moves over that bedrock, all of that debris that's in it scratches away the bedrock into place. In this case, this is a limestone rock that when it's eroded by the glacier, leaves white scratches behind it. And these white scratches are literally those rocks being dragged across. And it's very similar to what you imagine when you sandpaper on a board. It's just moving this rough material in one direction. It's scratching it away. You can tell from these striations. So if you see them, we were just talking about there's parts around here that have these. You can figure out what direction the ice is flowing. You see it, you know that the ice was going one of two ways. It was either going this way or that way, right? It wasn't going that way because the scratches are all orange in that direction. That's in fact how T.C. Chamberlain figured out there were continental scale glaciers. He went all over Wisconsin and the upper Midwest and Ohio. And he looked at all these striations and he figured if they all pointed back to the same area, there must be some huge glacier flowing up, producing all these striations over huge bands of them. And so you can imagine it from the side like this. If you look at the side, here's one of these rocks or a glass, and as the ice is flowing along, it's being dragged over the material. We can do this in a lab too. So we built machines in labs that allow these scratches to be created in a lab setting where we have things really well controlled. And then we can, when we understand how they are created in a lab, we can go out in the field, we can measure those ones in the field. And we know what the glacier did. We know the stresses that it put on the bed, how it grinded, that's what it.
Does the glacier scrape the bedrock on both the advance and the retreat, or just the advance?
That's a good question. So one really important thing to remember is that even when a glacier is retreating, the ice is never flowing backwards. Just like a river, the water in a river is always basically going one direction. When you see that margin retreating, it's just because there's so much melting at the front that it's outpacing the rate at which you're putting ice in. And so the glacier is simply retreating, not because the ice is flowing backwards, but because it can't flow enough ice in there to make up for it. So it only goes one direction. Yes. Here's some striated bedrock in Switzerland. You can see these big lines in here. See how it's relatively smooth. Just like sandpaper, the reason you use sandpaper is to smooth out a board. The glaciers smooth out the bedrock after they've had a lot of time abrading. Here's another example. This one's polished so finely by that material that's in the ice that it's like reflecting the light like a mirror. So we call it glacial polish because it's so smooth from that material grinding it down, just like you use finer and finer material and sandpaper to get a smoothness to the texture. Same thing. You can get these cracks that form. Sometimes if you have a rock at the ice bed interface and it's being jammed against the bed by the glacier as it's being shoved forward, it'll get stuck here. It'll get stuck until the rock underneath actually yields. It fractures. The fractures look like this. They're expressive. So you can get some where the lunate fractures where the horns point down ice. You can get other ones that are also the same general shape, but the horns point up ice. And there's some examples of these. If you ever been to Red Granite, Wisconsin, there's a bunch of these preserved around there. In that area when these fracture processes take place. So here's a sort of a cartoon that shows sort of the spectrum of these. You can get these different fracture patterns from ice being stuck
fracture in the ice, popping ahead, doing it again, doing it again. You get these striations, or you can get polish where it looks really reflective. And it just is different patterns of that material that's stuck in the basal ice being dragged over the underlying bedrock, smoothing it over. The other way that glaciers are able to really effectively erode bedrock is instead of slowly polishing it, they can crack off big chunks, right? So in this case, imagine this is the bedrock of the glacier. You're looking at it from the side, the ice is going this. The ice is literally ramped off of these areas, and it forms a cavity. And why that's important is it concentrates all the stress of the glacier, all the weight that normally would be distributed over this entire region on just this small part, right? It's sort of like if I stand here and I pick up 1 foot, now I've got double the pressure on my 1 foot. If I were to somehow be able to go up on 1 toe, I could put so much force on that 1 toe that I could break my bones, right? That's basically what's happening. As the glacier moves faster and faster, and the ice gets concentrated in a smaller zone, eventually there can be so much force on this area that it actually breaks the underlying rocks. Right? And so when you look at the escarpment just to the east of here, that's what's happened. It's part of the reason it's so steep is that it has been quarried and plucked away by processes like this as the glaciers advance over that region. This leaves, instead of smooth landscapes, really sort of jagged landscapes. Because you're not polishing the rock, you're literally breaking it apart and then taking those chunks and the glacier will pick them up and move them along. And that's what it uses to then try the bed. They're sort of reciprocal. So abrasion and quarrying produce sediment at the base of the glacier. The glacier then moves that sediment around. Right. So when we're in a place like Wisconsin, there's some evidence of quarrying and abrasion, but in lots of instances, the bedrock isn't that close to the surface. It's buried under all the sediment. What's happened is the glacier has eroded the material. It's made the sediment that we're seeing out on here, but then it's moved it and piled it up in certain places and dug it on other places. Well, how does it move the sediment that it makes? How does it move the sediment that it makes before abrasion? There's basically 3 processes. So when you look at how a glacier behaves, this is again looking at it from the side. The ice is moving ahead over time. So just like in that picture, you could probably have sediment in the ice that's carried along with the glacier as it moves. Believe it or not, at the bottom of most glaciers that are moving fast, there's liquid water, right? It actually warms up in the glaciers to get closer and closer to the bottom. And so there's like rivers running at the bottom of many glaciers. Basically, all fast-moving glaciers have rivers at the bottom. Just like any river you can see here, within a flood or whatever is carrying sediment, that water that's moving at the bottom can carry sediment. And then one other thing that's interesting is that the bed is made up of dirt, it's made up of sediment, and the glacier's overriding it, it can move that sediment along with it, sort of like a bulldozer, it can push it along over time. So these are the 3 main ways that the glacier is able to move that sediment: through the ice flow, through water flowing at the ice bed interface, and through actually deforming the bed if the bed is made up of sediment, which a lot of times we call till. So this is just cartoon or pictures of these things. Dirty basal ice, you can imagine if this glacier moves 10 feet, all the sediment that's in here moves 10 feet with it. This is one of those rivers coming out of the front of the glacier. You can see the water looks almost like milky. That's because there's so much of that fine ground up material from abrasion in it that gives it this color. If you're ever in a glacial region and you see streams like this, you should not drink this water. It's going to make you have a very sick stomach, right? If you do it. So we always have to take exorbitant measures to filter in the water just to not drink so much sediment that is in the naturally. And then you can move the glacier along. So this is a picture from an experiment that from the machine I built in Wisconsin that actually slides ice over till, and you can measure how much till is fluxed along the bed over time. This one's harder to see. I can't show you a picture from underneath the glacier. I can show you a little movie from these machines. So here's the clean ice moving that way, till it's underneath it being bulldozed along by the glacier. Now, when it drops that sediment off, we kind of get 2 main types of deposits in a place like Wisconsin. We get one thing that's called till, And that's unsorted sediment. So imagine you have that basal ice, like I showed in that picture. And it's got all that sediment, right? Big particles, small particles. Beauty about glaciers, they don't care. They'll pick up anything, big and small. They move it along, and then it melts. Well, what happens? It's just going to dump everything out. It's not going to sort it. And by sort it, I mean put like-sized particles by like-sized particles. It's just going to dump everything out. So that's why if you go out in your backyard here, unless you go right downtown, you dig a hole, you probably see like this. It's a real pain to dig, right? You dig, it's fine grain, then you hit a giant boulder, right? Or you hit a giant rock. And that's because that was material the glacier was transported, just dropped right in place. And we call it unsorted because you'll have big rocks next to tiny particles. The old name for this used to be boulder clay because you could find boulders next to clay-sized particles. And clay-sized particles are the really small ones you can't see. The other version of this is if the sediment is not being transported by the ice, but is instead being transported by that water, and then it's dropped out, it does get sorted. That water will put a like-sized particle by a like-sized particle. And so you can see something like this, and we call it outwash. It's material that was deposited by stream that were washing out from underneath the glacier. So outwashing the material from underneath the glacier. And it's pretty well sorted. You can see this nice stratigraphy in here associated with streams. I've been right up on the escarpment right here where a lot of those big windmills are. They're anchored into this type of material. That's what's on top of the escarpment. So if you want to build a road, you want to find this because it's already done all the work to sort the material for you, or if you're trying to put some driveway or something. If you find this, it's a real pain because you've got to sort it yourself to get the precise particle you want, where nature's done the work for you. So this is the old and pretty much the most up-to-date map of the glacial geology of what's at the surface in the upper Midwest. And it's color-coded here by the different types of sediment. So till is that material that was laid down. Outwash is the material that was deposited by like those rivers that were coming out the front. Ice contact outwash is just another version of this. And glacial lake deposits are things that were deposited in big lakes that were in front of the glaciers. And so everywhere that has a color on here was influenced and it has sediment that was deposited by glaciers. What you can see is the entire upper Midwest. Their lakes still have it. It's just we don't know what's under the lakes. The only piece that's missing is this little part right here. It's that driftless area that I was talking about. Everywhere up in every other place in the upper Midwest, everything you see on the ground was deposited in some way or shape by glacier. It could have been reworked after the glaciers left, but that's originally how it got here. Right in Fond du Lac right here. This map's not in detail, but I'll show you the next one. There is these glacial lake deposits right here where the footprint. This is the updated map. It's just Wisconsin. It just came out a couple months ago. It's like I'll probably use it in field trips for the next 20 years of my life. But they went through and they took all the maps they had made of the whole state and they put it into this one nice cohesive map. But you can see the outprint of those lobes, like I was talking about, the Green Bay lobe, the Lake Michigan lobe, these more northern lobes. They color coded it by the
Point out where the escarpment is on.
Yep. Yeah.
I feel like it should be a line and there's just not a.
It's right here. The thing to remember is this isn't the bedrock. So it's not like the intact rocks of the escarpment. It's the glacial deposits that are on top of the escarpment, right? And so the escarpment is almost completely covered with till. And so what it's showing here is till. If you had another map of the bedrock, you'd see the escarpment right through, it goes up and ranks 9 balls. Okay, so we can grind rocks up, we can move them around these different places. Who cares, right? Well, the reason we care is because they make all this cool topography, right? They make the landforms we see in Wisconsin. They dictate where you can have a farm that won't be successful, where you can have a farm that won't be successful, where you put a gravel pit, where you can put up down a water well and have success, and maybe put down a water well that's contaminated, right? And all that's dictated by these types of things. Like I said, I'm going to break this into two parts: subglacial landforms and proglacial landforms. So in this cartoon, this is my crappy attempt of drawing a glacier. Imagine this big ice sheet is flowing here. We're right at the margin or the end of the glacier. A lot of times we'll call this the margin or the terminus. And so first, we're going to talk about things that are made underneath the ice, things you couldn't see. If you went to a glacier in Alaska right now, you wouldn't be able to see them. They're happening, but they're just out of sight because they're underneath the glacier. They're subglacial. What do they look like, right? Now we see them on the landscape because as the glacier melts, it leaves behind all of these landforms that it was making underneath it. They're interesting to live on. For someone like me, they're interesting to study because if you could figure out how they're made, they tell you something about the processes of the glacier, how they work. And those are applicable here, just like they are in Antarctica, just like they are in Greenland or in northern Canada or wherever. One common deposit is something called the glacial erratic. What is it? It's just a big rock, right? Or a rock that doesn't belong there. What I mean by doesn't belong there is that geologists can look at a rock and they can identify what type of rock it is. Granite, is it basalt, is it something else? And if you look at this and you say, okay, this rock's granite, but there's no granite around here at all, right? The next closest chunk of granite is 600 miles away in Canada. How could this thing have gotten? There's no way that a river could carry it that far. And so what's happened is the glaciers have picked up these rocks that are of a different lithology, of a different rock type from very far away. And over time, maybe it's thousands of years, maybe it's tens of thousands of years, have slowly conveyor belted those things from up near Hudson's Bay and dropped them off in places like Fond du Lac and Madison. So this was a big erratic. It was on UW-Madison's campus. It had this plaque for T.C. Chamberlain associated with it. If you've been to Madison and you've been up at Picnic Point, you've probably seen this wall that is like the entrance to Picnic Point. And if you look at all the rocks in it, one thing that's kind of interesting is the rocks that make up this wall are not rocks that you find anywhere near Madison. They're not even rocks that you find up here, right? They're rocks from like northern Canada. And so what they did was when they were building and maintaining the trails for Picnic Point, they picked up all the erratics and they made this entry wall to it. So much so that because we can't give exposure to these types of rocks to our undergrad students, we can't send them out to Canada. What we do is we send the huge classes of hundreds of students to go out and just look at this wall, with the map of what all the. First, we send them out there with the map, although I'm pretty sure their phones just figured out by now. They go out there and they try to look at the different rocks and identify them because it's such a wide smattering of the rock types from this whole part of the country. The glaciers sort of concentrated in this area and they built a wall.
Those cleaned up before they were set into the wall.
Nope, they just set them in there. Yep. There's probably a lot more bigger ones than they left on. They probably selected the ones that were about the right size. So what about how does this subglacial landforms, how are they created from, in particular, water flow? And I said that water can flow to the bottom of the glacier. And not only does the water flow, it moves sediment around and deposits sediment sometimes. So we have these distinctive landforms that are left behind that are associated with water around the glacier. So this is a river that's coming out from the front of the glacier. But if I were to go peel it back, it looks something like this. It'd be this long tube that could go maybe a mile, half a mile up under the ice. And it's conveyor, it's transporting water along with it. But not just water, it also has sediment. So in some cases, it fluxes all that sediment up to the front. But sometimes it can't. It doesn't have enough energy. The water's not moving fast enough to carry all the sediment that's supplied to it. So sometimes the sediment gets deposited in the channel back up under the ice. In fact, only the smallest particles get carried all the way to the end. The bigger particles get sort of left behind up under the ice because the water is moving fast throughout there. It leaves it behind. So that channel forms something called an esker. So here's a little cartoon of it. So imagine this is the ice. This is this channel running up under the glacier. And over time, it's carrying this water, but it's depositing sediment in the bottom, just like a regular stream like you'd see around here. But unlike a stream that you'd see nowadays, the banks of it are made of ice, right? They're being confined to it. So you're building up this bottom of the channel over time. And you can imagine that if you were to then melt away all this ice, what would you be left with? You left with the bottom of the channel on the surface. So you get this long, sinuous ridge that represents the bottom of a river that was under the glacier. But this river, instead of carving down into the ground, built itself up and up and up, right? Here's an example of one of these in Iceland. So you can see that this is just tracing the footprint. You know, it's probably 2 or 3 miles long of a river that was under the ice when this section of the ground was under the ice. We have those all over in Wisconsin too, these estuaries. There's several of them in Fond du Lac County, specifically in the south east part of the county. There's 2 or 3 really big and south, much bigger than this. They just have a lot of trees on them, so you might not notice them, right? Yeah. Another thing that can happen is sometimes instead of the water flowing out from the bottom of the glacier as this nice, peaceful, constant river, it comes out as a giant flood, right? Like think of it as the river's not there, not active at all for 10, 20, 30 years. And then there's a flood that drains basically a lake's worth of water over the span of a couple of days. And when it does that, the flood, instead of depositing sediment, building up the base, it actually cuts down. And so this is by Stevens Point. There's this big feature called tunnel channel. And that's what these are. These big linear scars on the landscape here represent these absolutely massive floods that were created because a big lake of water that was underneath the glacier here drained out suddenly and cut these channels. Right? And so these channels can be 15 kilometers long, so they're 10 miles long. And they can be hundreds of feet deep and like a half a mile wide. So they're absolutely enormous channels that are cut in the span of like 2 or 3 weeks. Right? When these are flowing, there's more water coming out of one of these than the Amazon River. It happens to be concentrated in this one spot. And so people around Stevens Point have gotten wise to this. And at the end, so this is right where the edge of the glacier was at. All of these floods are depositing material out here, and they've mined it, right? They're mining it for the gravel and sand. And then all these deep scars here, that's where all the lakes are around Stevens Point. So this is sort of the most highly sought after land in the area because it's where all the lakes exist and people build their houses along these, or what they're called chain of lakes. They're in the footprint of this country. So what about this till deformation? The ice moving over the bed, bulldozing the sediment from place to place. That makes it probably the most famous landform. Well, the landform that Wisconsin is the most famously known for, which is the drum. Right? And so here's an example of one of these. What is it? It's a hill. It's elongated one direction. In particular, elongated with the ice. What's happened was this was made under the glacier. And as the ice was advancing, it was deforming sediment underneath the glacier. And on the sides here, it was deforming the sediment so fast that it was picking it out, picking it out, picking it out, faster than sediment could be carried in. So on either side of this, the landscape was lower at the time, right? Now on the drum itself, that sediment was being plastered on, plastered on, plastered on. So in the middle, it's railing up. But the sides are going down and the middle's going up. And the longer you expose over this, the more it takes this thing and streamlines it, like an egg or kind of like an airplane thing. It makes it in this elongated direction because the ice is constantly flowing around this thing, moving the sediment. So these areas have been eroded and been causing. And we've mapped 15,000 of them just in the footprint of the Green Bay lobe. They're in other countries, they call these Madison type drumlins, just the drumlins, because Wisconsin in the Green Bay lobe, where we are right now, is the best example of it in the world, right? It's where people come from all over the world to Wisconsin. Well, maybe not all people, but geologists the world. That's also the thing that most good geologists like to fight about the most is how these things are constructed. And so that's why they come to Wisconsin to fight with each other.
Geologists disagree.
Yeah, I know. So
Northern trails in Madison.
Yep.
Is that part of what you're showing us? Is that what you would see when you were out there on the trail?
yeah, you would see it. Yep, they're on all the sides. There's a huge drilling field about 2 miles from here, right on top of the escarpment. All of the big hills, those are all drumlins. Those are the tallest drumlins in the state, are the ones that are right up. I have some figures of those to show you. So, yeah, the drumming field here that was close to us is called right now. It's called the Campbellsport Drumming Field. And it's probably the second most famous drumming field in These are what these things kind of look like, right? They're, if you look at it from above, they're high in center and they get low as you move away, and they're sort of elongated in this teardrop shape. They don't necessarily have to start like this. They can start closer to like a round shape. But as the glacier continually flows over them, shapes them, moves the sediment, that sediment deformation, they slowly get longer and longer and longer, sort of narrower. So when you look at the drumlins that are south of here, but not on the escarpment, they're super long and super skinny. Like sometimes they almost look like railroad tracks are so long. Like this one, right? So here's one that's very long, very skinny. It's convenient because they're harder to farm. They have all sorts of those big rocks in them. They're gnarly. They're because of the way they're perched, it's harder to pump water out of the ground there in some respects. And so they don't get farmed as much. So they show up when you fly over them a lot of times because they got trees. You can farm them. A lot of this is small work. Here's another one that's more sort of equine. Again, the ice in this case is flowing this direction, but you can see it's a lot wider than it is longer compared to that last one. That's because this one hasn't had as much time under the glacier. The glacier didn't do as much to shape it. Yep.
So is the genesis of a drumlin, does it come down to the composition of the bedrock, or what causes that?
So most of the drumlins in Wisconsin are cored with till. So there's not bedrock inside, it's sediment, just like I showed before. And not to get too much into the details, but what happens, or what we think happens, is when the ice advanced over the landscape in Wisconsin, the ground was frozen before the glacier advanced. So it was permafrost, and the permafrost was hundreds of meters thick. And as it started to warm up, some spots warmed up faster than other spots. In the spots that stayed frozen, you can imagine if I gave you a chunk of dirt and I put a bunch of sediment in it, I put it in your freezer and froze it solid. I said, here, I gave you that one. I gave the person next to you the same thing, but I didn't freeze it solid. I said, squeeze it. The one that's not frozen here is going to be able to move around, but the one that's frozen solid is going to be really strong. And so what we think happened is the core of these things are the spots where the ice didn't melt out, and they were extra strong. And so they were able to resist erosion. Whereas the sides melted and the material was more easily excavated away. And once that process started, where this became higher, this became lower, sort of a positive feedback cycle kicked in. They kept this part growing and kept this part being eroded. Yeah.
What would cause the sediment to melt unevenly?
It would be because of the water flowing through the bottom of the glacier. So imagine a river kind of can flow in like a network of streams. So if you have rivers here, this part would melt, and now the river here, that part is frozen. Yeah. So it has to do with how the water is moving. Sort of in a patchwork. Yeah.
So they purposely are doing it differently.
They're mowing it like this to help me out, so I can show this. No, they're doing it to preserve the soil. Yeah, if they this is called contour plowing. They're doing it so if you just plowed it like this, you would carry the topsoil down the side. So they're doing it smarter to the same. Yeah. Yeah. No, we always say thanks to them for doing it. But they're doing it at the same time. So, yeah, it's another big one too. So here, this is just the greater area. So we're right here, right now, right? You can see it's really flat. Here's this Campbellsport drumlin field that's up on the escarpment. Here's the main Madison type drumlin field where there's 14,000 of these things. All these little dimple marks you can see here, every one of those is a drumlin. And they stretch all the way from here, all the way down to basically the margin of where the glacier stopped. There's Madison, that's about the edge of where the drumlin. Here's Madison, this is the isthmus. This is where the Capitol is. The Capitol sits on a drum, and that's why it's high up. Bascom Hill on our campus. Everything you see here that's a bump is a drum. If you're in Wisconsin and you see some topography and it's not the Niagara Escarpment, if you're anywhere other than Fond du Lac, it's probably a drum. But all these little bumps here are drumlins. This is just zooming out a little bit. So here's the isthmus of Madison, Monona, Vermintota, Monona. But you can see all these fingers here. Those are all drumlins, right? They're all aligned in the same direction because the ice was flowing this way and shaping.
How would you know the difference between the Indian burial ground and the state?
most of the time the burial mounds are more conical in nature, unless they're shaped like an animal, or they're shaped like an animal, and they're way, way small, right? So a burial mound would be, like, for example, here would not be even as nearly as big as just the capital, right? The capital is way bigger than a typical burial mound, so that they would be a little, well, scale. These are a lot bigger. Okay. Another thing that you can get is something called a cane. So imagine the glaciers like this, and you have sediment on the top. Sometimes we get these pipes that open up from the surface of the glacier all the way to the bottom. Sediment that's at the top can get washed down there. Just like an hourglass, it builds up this big mound. So if you've been just a few miles away here, Dundee Mountain, is what this is. It's a big pile of sediment that is poured through the glacier and built up like an hourglass over time. Once the glacier melts, you're left with that sort of conical, something like this. So that is Dundee Mountain. This is a version of one of these things on a modern day glacier in this one's in Iceland. Granted, the ones in Wisconsin are way bigger than anywhere else in the world, and we don't exactly know why. They're about 10 times bigger than anywhere else we've ever seen. Dundee Mountain. Yeah, probably the glacier was so much bigger than what happened. Pro-glacial landforms. These are things that are made at the front of the glacier, so no longer underneath it. But if we think of that glacier being here again, what's forming right at the edge, at the margin, and outboard. So here's a picture looking down. Here's this glacier right here. Here's the edge of it. And if you look in front of it, there's all this sediment, right? And you can see the river, and great channels, and all sorts of things like that. This is all in this area right here, sediment that's been washed out into the glaciers, outwashed corner. A flat plain sediment, sort of like a river delta or a river plain, was made by this coarse sediment being washed out of the glacier. In that outwashed plain, you can have chunks of ice that get left behind and buried by sediment. So imagine the glaciers here, and it leaves these dead chunks of ice, which happens pretty good. All the while, the water is still flushing sediment out of the front and starts to bury these chunks of ice. And then if they melt, you're left with a depression landscape as you melt. Analogy I like to use: you put a balloon in a sandbox, you level the surface, it looks perfectly flat, but then you pop that balloon with a needle, what's going to happen? Then you're left with a depression. When you talk about the kettle moraine, why the reason it's called that is because it has thousands upon thousands of these buried ice blocks that were melted, left these depressions, left these kettles all over the landscape. Over there. Another thing that can form in this similar type of way is instead of the ice being buried by the sediment, the ice can actually make the banks of a lake that's on top of the ice. So here is a lake, here's the ice right here, the banks of it, and this is all sediment that was put on top of it. Then as this ice right here melts, the sides let down, and you're left with a flat lake that previously was the lowest point on the landscape, now the highest point. So you can call this a topographic conversion. And you can have this ice walled lake front. So you have these. Everything I'm showing you here is in Fond du Lac. It's pretty amazing. It's big here, right? And this is what they look like. This one from northern Wisconsin. In northern Wisconsin, the farmers have gotten wise to the fact that basically they can't farm anything other than these, right? And so when you go up there, you'll see these farms that are out in the middle of fields of trees. It's because they're built the farms on top of those flat ice walled lake. Now, a big feature, maybe the main, in that instance, you have the glacier coming out of the landscape like this, and it would have stopped right here. Just like that video I showed before in Asia, the glacier continually conveyor belting material toward the front. What happens is when that sediment gets to the front, that material gets to the front, it just dumped into this big pile. And here, you can see this big pile right here. It's basically tracing the outline of where the glacier sat. Now, the glacier has to stay there for a while because it needs time to conveyor belt enough material there to build up. So if the glaciers keep moving around, it doesn't build a big moraine. But if it gets to some spot and the climate's stable for a month, maybe 100 years, maybe 1,000 years, it can conveyor belt all of this material here, build these big moraines. Something like this. So here's the glacier. flowing here, dump all this material at the margin, glacier melts, but we're still left with this pile of material called the moraine. So here's a picture from the side of the glacier. It just shows all this material, debris that's on the top. That's being dumped into the moraine. Material that's coming from the bottom being put in the moraine. We're stuck in the ice that's being put in the moraine. Everything is dumped. So you can have different types of moraine. So what we generally do is, in this case, you can see the glacier right here. It was flowing this way. And this moraine right here is as far as it got. So we call the most outboard moraine, the farthest extent it got, the terminal moraine. But it can pause at different instances as the glacier retreats, and it makes what are called recessional moraines. So in Wisconsin, we have one terminal moraine that's down by sort of Madison, and then we have tens to maybe 100 recessional moraines all throughout the state as the Green Bay will pause in its retreat. So here, I'll play this movie again. This is that same one I showed you before. But every time the glacier hangs out in a location for a little while, it lays down another moraine. So this is the terminal moraine, the Johnstown moraine. But then you have a series of moraines as you move towards the north that are associated with other time periods where the glacier sort of paused and hung out in that location. Yeah, again, many of these in Fond du Lac County. I'll show you a picture of maps of
So if it creates a terminal moraine and then goes back over the top of that, is there an easy way for you to tell that that there used to be a terminal moraine there and then it grew back? Because there's a couple of times where like it stopped, stayed there for a while, and then went all the way back to Madison. Can you still see any evidence of that former terminal moraine?
most of the time not. And then if say the ice advanced to this location and then retreated, then it re-advanced to this one, that would no longer be terminal moraine. It just would be whatever the farthest one.
And does the other thing, can we find any evidence of that previous moraine?
Sometimes in Wisconsin, the Green Bay was so powerful that it overrode most of them. But in Iowa, it did. And you can see the preservation of older moraines that were deposited and then over by what's called the Des Moines War, which is the main interactive in Iowa. So, and that partly has to do with the fact that the ice or the ground in Wisconsin was frozen when it overrode it. And that wasn't the case in Iowa or Michigan, or basically North Florida, some. So you probably heard of the Ice Age National Scenic Trail. What it is doing is following that terminal moraine. That's what the trail does, right? It follows the terminal moraine throughout the state. It takes a couple of jogs in other places to go to, especially the full thing, like around Devil's Lake, other places here around Interstate Park. But for the most part, the reason that the Ice Age Trail exists, or where it exists, is following this terminal position. Yeah.
Do you have a suggestion on which direction is best for that to take that trail?
I don't. I like a lot of it, but only in this part, and I've only sparingly been up here. Yeah. A lot of times I work back in this part where it's messy and dirty and blood, mosquitoes, right? Especially up north because it's like the ground's very wet. Okay.
Really big differences and changes and sounded for
Well, the glaciers are integrating weather over a long period of time. And so as the climate changes, they'll start to get surface melt on the top. And the surface melt is important mainly for one specific reason, that it can go through those tunnels all the way to the bottom of the glacier. It can add more water to the bottom. What that does is it can actually float the glacier up, sort of like an air hockey table, and turn the air pressure up and cause the glacier to sort of float off the bed. So that's the main way right now that you can influence the dynamics of the glacier. Okay, so the other thing the glacier is really good at is making lakes from it. The reason is, imagine you have a river here and there's no glacier. The river wants to go this way, right? It wants to carry the water that way. But if you put a big glacier here, it blocks the way the water wants to naturally go because of the landscape. And so it builds this big, what we call proglacial lake in front of it. And as the glacier retreats, the proglacial lake moves with it. So a very big example of this is this main basin of Glacial Lake, Wisconsin, which is a lake that doesn't exist anymore, but was here because the glacier sat in this area and pinched off the natural drainage of the Wisconsin River, which normally goes around the Baraboo Hills and out to the Mississippi. But because the ice sat right here and pinched it off, the river couldn't drain the way it normally wanted it to. And so it built this giant lake called Glacier Lake, Wisconsin, until the water got so high that it was able to basically drain this way. Just for the sake of time, I won't go into too much of this, but what happened was when this lake catastrophically drained, that's what made the Wisconsin Dells. The Wisconsin Dells formed because the glacier pulled off of here just enough that this whole lake drained in the span of like a day or two. And this pinch point right here where all the water got funneled through, it buzzsawed into the underlying ground. And that's what cut the Wisconsin Dells. The Wisconsin Dells were cut in the span of a couple of weeks, not a long period of time from that lake draining. We used to think it filled and drained multiple times, but now we think it was just one time. So here's a picture of this main basin. This main basin, the ice pulls back, forms a secondary basin, just opens this pinch point, it drains. The main basin drains into this smaller basin, then cuts through this area as it does the Wisconsin Dells. So all these slot canyons you see here, that's one of my kids. In this canyon, that was carved in just a matter of days, weeks, essentially, from that lake drain. So
It's all sandstone, is right?
yep, it's all sandstone. So it's easily erodible.
What made people realize that it all drained in one day versus filled and drained the multiple times?
Yeah, this is kind of hot off the presses stuff, but what up in here, the Geologic Survey, the Wisconsin Geologic Survey, has been drilling cores into these, and they found these very thick packages of sediment associated with the filling phase. And at the bottom, they found pine needles, and they can date those pine needles. And then because of the date on that, they know that everything above it has to be younger than it. And the dates of it mean that basically it only could have had time to drain once. Yeah. So it's not, I don't think it's like quasi published research, but it's very well detailed. Yeah. Okay, so in this area, as the ice pulled back, we have this large lake called Glacier Lake Oshkosh. Lake Winnebago was part of it. So I'll show a couple more slides of it, but the same general thing happened. The water wants to drain to the north here, but the big finger of the Green Bay lobe that's still left behind is blocking it. And so the whole region starts to flood. And as the ice retreats, the lake kind of follows with it. Eventually it starts cutting across the Door County Peninsula. And if you've ever seen, you know, you don't go to the Door County and it's flat, and then you drive way down into the valley where the towns are and come back up. All of those low spots are because Glacier Lake Oshkosh buzzed across the Door County Peninsula and cut those channels out. So they're all because of this lake that was impounding water in what we are right now. So we zoom in on here, doing a little bit more here. So this is where we are. This blues here are sediments from the glacial lake. The whole city, probably why they built the city here, is flattest part, and it was pretty stable because this was underneath one of those lakes. The sediment just kept filling it in. And that's what makes the landscape relatively flat compared to what it's like. Here's the escarpment, and up on top of the escarpment, and this. I'll show some more stuff too here. So this is one of these shade relief maps for Lake Winnebago. Here's the escarpment. Up on top, you can see all these drawings that I was showing you before. It's relatively flat down here. This is what we call the Green Bay lowlands right here. This is an area that was very heavily eroded, and then that lake filled it back in. If the lake hadn't been there and we hadn't filled it in, right now we would be under the water in Lake Winnebago because the lake would have extended at least this much farther into the center. So right there's Fond du Lac County. Here's the Green Bay Road. And you can see that we're basically under the quicksand. This fact is kind of cool. These are all the moraines that are left behind. These are all the places that the ice paused in Fond du Lac County. So here's one of the moraines. This St. Anna moraine. The Erie domain is the big important one. That's where the footprint of the lake basically starts because the glacier stopped right here and built a lake out in front of it. Then as the ice retreated, it built another lake in this area. So this is the depth of sediment that was laid down. So these dark areas here have over 30 meters of sediment until you get to the bedrock. And so in this area, there's all this material that was filled in because there was a big channel that was carved into the bedrock. And then as the glacier and the lake was sitting here, it filled it in, filled it in, filled it in with over 30 meters, 100 feet of sediment. You have to drill very deep right here to get to the bedrock. Whereas if you go 2 miles up the escarpment, it's only a few, 6 feet or something. The drumlins in Fond du Lac County are interesting because the low part of the county where we are now has drumlins that are oriented this way because they were shaped by the Green Bay Lobe flowing largely to the southwest. But when you get up on top of the escarpment, you can see they're oriented in a different direction. And that's because when the ice had to struggle to get up over the Niagara Escarpment, it was flowing not to the southwest, but it was actually flowing to the southeast. And that's reflected in the orientation of the drumlins that you can see. So these are not part of the county. This one is up on top of the escarpment. This to me is one of the cooler images. So this is 15,000 years ago. Here's what's left of the Green Bay Lobe. It creates a glacial lake called Great Glacial Lake Fond du Lac, right? Then that lake is spilling water. This lake is higher than the dome, but it spills water into these other lakes and moves along the edge of the lake. Then, as a final one, when the glacier retreats a little bit, up basically into Lake Winnebago, you have this connection of this big glacial lake that was over here with Glacial Lake Fond du Lac. You make this much bigger lake called Glacial Lake Oshkosh. All the while, sediment's going into there from the front of the glacier, and that's what building up the base. That's what's building up the ground that we're on right now. The sediment that was dropped into this big glacial lake Oshkosh. Down in the south east part of the county, we have these big esters that are associated with the kettle moraine. Those are again these big channels that were at the bottom of the ice. In some instances, let's say they're several miles long, right? That are forming. That channel is carrying sediment and staying deposited into it. And then as it melts, it leaves behind just the high part that was the bottom of the river that had the walls made out of ice that were confining it. Now, the kettle moraine is much the southern part of the county. But what it is it's an interlobate zone. It's where that big Green Bay lobe runs into the Lake Michigan lobe. It's what we call an interlobate area. What it would have looked like is kind of like a McDonald's arch, right? If ice is flowing like you would have these two high parts and then a low part. And the kettle moraine is in the low part like this. What happens is sediment is flushed into that low part, the lowest part, off the top of the glacier. And then as it melts, the sediment actually helps protect the underlying ice from melting. It insulates it, like how they used to put sawdust in ice boxes to like keep the ice from melting. Does the same thing. It makes this really high part on the landscape. Some of the sediment goes through, makes canes and things like that. But what happens in this part of the kettle moraine, the northern part of the kettle moraine, is different from the southern. That sediment gets so high in the landscape that what we think happens is it spills off into the sides. And it makes these two moraines. So if you've seen around Dundee, there's that flat section with those big mountains in it, Dundee Mountain. That's this part, right? What you're seeing is the moraine associated with the Green Bay lobe side of the region in the Lake Michigan lobe, and this flat section in between. But in the past, that flat section was actually the highest part of the landscape. It just spilled all the material off to the side because it was the highest. In the southern kettle moraine, we don't have it. We have just a single moraine, single bill. But up in this part, it does this. It executed this more complicated wasting away that caused it to have a double. Okay, so no, I'm just over time. Sorry, but I'm happy to answer any questions. So stay as long as you want to. Thanks for coming though. Yeah.
Moraine. The escarpment was labeled and it looked like it had a moraine. Was it a moraine or is it just something else that is it one of the like the cavity break off thing that you talked about? It was the other one.
This one?
No, the zoomed in Fond du Lac. Right?
Oh, I see.
No, back to it.
Oh, sorry. This one. Yeah, so this is a recessional moraine, but it's not the one that actually divides. The kettle moraine is right here. The Green Bay lobe is able to get actually up the escarpment. Even though, okay, so from like, imagine the glacier is like a mile thing. And the escarpment is big, but it's not huge. But it was enough to redirect the flow of both of the lobes in this entire area. It's the most important thing for directing ice flow in Wisconsin, is the Niagara Escarpment. And what it did was the Green Bay lobe was coming down this area, but the dividing line between the lobes isn't the big escarpment that you have out your backyard. The Green Bay lobe was actually able to get up and over the escarpment and go this far to the east, which where it's not. And so what you're seeing here is a recessional moraine associated with when the Green Bay lobe got smaller, it sort of shrunk in like that. And what you're seeing is the edges of it come in sort of like this.
So the escarpment, so the glaciers didn't create the escarpment.
No. The escarpment is millions of years older than the glacier. Yeah. The escarpment it actually, you might know this, but the reason it's the Niagara Dolomite. It wraps all the way around here, goes to the Upper Peninsula, Michigan, and makes up Niagara Falls. Right? And it's basically like if you look at Michigan from space, and then you can see geology somehow, it would look like a big bowl. It's called a basin. And if you would think of the edge of the bowl, it would make like a circle. And what you're seeing is the edge of that circle right here. That's because the Niagara escarpment is a particularly erosive, resistant to erosion. So the glacier wasn't eroded nearly as much as it was the weaker shales that are here and the weaker shales that were in Lake Michigan. The reason Lake Michigan is there is it wraps around Michigan with Huron. It is a weak layer in the hole that the glaciers have selectively carved out, just like this. But then you have the hard, resistant escarpment.
So the rock was there, but the cliff itself was created because the glacier could take out the ground from the other side of it.
Exactly. It eroded this weaker rock that was in this area. Yeah. Most of those are kettle plates, so they were formed by lots of the sediment being dumped and buried around these ice blocks. And if the ice blocks melt, it left a depression. And in this area, most of the time, the depressions turn into lakes because the water table is so high that it basically floods the depression and makes a lake. In some areas in like northern Wisconsin, that's not the case, but in this area, it's almost like. So there's some Long Lake. There's a debate about Long Lake, but almost all the rest of them are.
The continental ice sheet, big picture, it retreated toward Hudson Bay.
Yeah.
Right. So there must be some point where on the continent where the outwash is going one direction and then it changes direction, like because of elevation. Is there a name for that?
Yeah,
It's
it's not really a continental divide, but there is a drainage divide, and it's basically in very northern Wisconsin. So like the Gogebic Range that runs through the Upper Peninsula of Michigan, and it makes the Iron Range in Minnesota, and then it runs just south of Ashland. There's a big bedrock high that is kind of the natural dividing line.
Okay.
It's a little tricky because what happens is these glaciers are so big that they actually press the crust of the earth down in not an insignificant amount. If a glacier is 2 miles thick, it probably presses the crust of the earth down like 3/4 of a mile, right? So the land here would have been, we call it isostatically depressed. It would have been pressed down into the earth because of the weight of the glacier. And then when that glacier melts, the land starts to pop back up, and it takes thousands of years. And so right now, the land here is popping up about a centimeter every century, right? It's still popping up in glaciers. And up in Hudson's Bay, it can be up to like, it's 2 or 3 feet a year in some places, right? It's how fast they think in the past it popped up because the ice was so thick above that section that it's still popping up.
The central sands, was that one of them in that Lake Oshkosh busted out?
But central sands was formed because of Glacier Lake, Wisconsin. So right where that Glacier Lake, Wisconsin is, all part of the dells. All this, so this central part of the state has a really prominent sandstone area called the St. Peter sandstone, and that was chewed up by the glacier, and that sediment was washed out into the central sand and filled up the basin. So the central sands has something like 40 or 50 feet, in some places up to 100 feet of sand that was washed into it that originally began as a rock in this part of the state. And it happens to be so finely sorted that that's why there's all the sand lines in the central sands. It's perfectly sorted and it's perfectly the right size for hydrocracking. So when they hydrocrack the ground, what they do is they inject high pressure water into it. And they try to break the rocks. That allows the gas to flow through, but they don't want the gaps to close back up. So they inject sand in there to hold them open. And all over the world, or at least all over the United States, that sand is coming from the central sand. It's the perfect size. The glaciers eroding the sandstone that was under this part of the state where we are now.
And they're extremely round.
Yes, yeah. Which just makes it easier to inject, but yeah.
So on that same line, like Fond du Lac tends to have a lot of clay soil, is that all part of the together?
Yeah, the clay soil is all because of that glacial lake that was here. Because what happens is in some areas where a lot of times when you put sediment into a lake, the clays can stay what we call in suspension. They stay kind of floating in the water until the winter season when they rain, especially if the ice is, if the lake is ice, which she's probably doing. And so you get these big packets of clay. And you can actually, in some places in Fond du Lac County, see what are called bars, which if you cut a section of the lake clay, it has this striped pattern, which is a summer, winter, summer, winter, summer, winter pattern. So people will go and cut those open and they'll count them like tree rings. They'll say, okay, this lake must have been here for 8,000 years. So it's just 8,000 of these bars in there from it's basically a lake. So
And like you had mentioned earlier that oceans show the status, like Lake Michigan, you don't see any status.
you probably could, but people have not really poured into Lake Michigan to look at that. And so in the oceans, it's not so it's sort of the clays, but it's actually the organisms. The isotopic composition of their shells change based on the temperature of the water that they're living in. So the water gets colder or warmer, or there's more or less of it in the ocean. The calcium that they take out of the water to build their shells is a little bit different. With a lot of water in the ocean now.
As we're wrapping up, can I just ask you to let us know where we can find your work and where we can see you next?
Yeah. She's alluding to the fact that Nova's filming a show on what I'm doing. And so they're coming to Madison in a couple months, and then we're going to Alaska this summer. So I guess you can watch it on Nova. If you Google me, I got YouTube talks all over the place too on things related to this or things that got more mechanics and stuff like that. So there's that. The BBC filmed a show, but they only released part of it in the US. It is the part that I'm in, but yeah, they cut everybody else out.